Okay, thank you very much for the introduction, and thanks to the organizers for inviting me here to give this talk. Yes, so it will be about all those things that appear in the title. So there will be a bit of operator algebras, a bit of geometry, hopefully, topology more. And in particular, we'll focus on these algebras associated to subproduct systems that, yeah, they've been around for quite some time now, 15 years, but there's been increasing interest in recent years. So we'll discuss why I'm interested in them. So let me start with a brief sketch of what we will do. So I was trained as a non-commutative geometer in the sense of thinking of sister algebras as functions on some quantum space, whatever that means. So we saw this a bit also in Bob's talk yesterday, this idea of this underlying non-commutative spaces. And in particular, I will focus on examples that arise from algebras that are constructed for representations of group and quantum groups. Everything will be type A1, probably, in this case. So it will be nice to extend this to other groups, but more on this later. And I will look at sister algebraic extensions that I will interpret as some kind of boundary extensions, like the quotient algebra being the boundary of something that is in the middle. And then I will compute invariance. So, I mean, once you have the algebras, you want to know what their topology is. So we'll look at K-theory, K-theory, K-homology, and also Poincare duality. So, so the idea of this talk is, this should be the message for you, is I'm gonna start with my favorite exact sequence of sister algebras, because I think it's really the best exact sequence of sister algebra. It's a tuplets extension. And then I will extend it in different ways, and then hopefully you will get away the message that these subproduct systems that I will talk about in the second half of the talk are unifying language for describing this type of extensions. So what you see on the upper part, this one here is the tuplets extension. So it basically basically tells you that if you construct the tuplets algebra, the algebra generated by the unilateral shift, then this is almost commutative. It's commutative up to compact, and the quotient is a commutative sister algebra. And if you compute the spectrum, you get that it's a circle. So you can think of T as a non-commutative disk, if you want, and it's actually, there are people that define quantum disks. It's a long time ago. It's really isomorphic to a quantum disk. So you can think of tuplets algebra as being some quantum object, some quantum disk, whose boundary is the usual circle, so the usual boundary of the usual disk. And then you have this ideal of compact operators that makes this work. So you can extend this in two ways. Well, you can extend it in many ways, but these are two ways in which you can generalize this. So the first one on your left is the Kunz-Pimser extension for C-star bimodules. So here I wrote it under mild assumptions on the bimodule, so that the ideal is the compact operators on some Hilbert module. So you can think of this extension on the left as gluing together tuplets extensions along a C-star algebra. And that's actually what it does. And then I have another generalization, which is Arveson's tuplets extension for odd-dimensional spheres. So it's basically the same as what happens with the unilateral shift, but done in higher dimensions, so that you get a non-commutative disk whose boundary is an odd-dimensional sphere. So this is the examples that I have in mind, and then all these are examples of what I call the subproduct systems. So let's look at the first one. So I became interested in this one during my PhD, so now it's a long time ago. And so I'll just make a brief summary of why I was interested in Kunz-Pimser algebras. They are very interested in sister algebras because they have computable K-theory, and they appear a lot as a unifying language for different examples of sister algebras, like graph algebras, and algebras associated to partial automorphisms, and so on. But when we stumbled upon them, when I was working with Johnny and Simon, and then later with Jens, we were interested in line bundles over non-commutative spaces and in the associated circle bundles. So when you have a Kunz-Wieser algebra, these are defined as universal C-star algebra associated to a C-star correspondence. When your C-star correspondence comes from a non-commutative line bundle, or if you want, it's an invertible correspondence, then when you perform the Kunz-Wieser construction, you realize that the exact sequence in K-theory that the Kunz-Wieser extension induces actually agrees with something known from, sorry, it clicks without me wanting to click. Oh, okay, so this is a pointer, right? Okay, so when you construct a K-theory exact sequence induced by this extension, it gets this very nice form. So the map here, well, first of all, you can identify the K-theory groups of the tuplets algebra and of the compact operators with the K-theory of the coefficient algebra, and then you get an extension that has this form. It only contains the K-theory groups of the coefficient algebra and of the Kunz-Wieser algebra, and you have this map appearing 1 minus x, and this is really the same as the Euler class of a line bundle, which is alternating sum of the identity and class of the line bundle. So if you interpret your Kunz-Wieser algebra as a non-commutative circle bundle, this gives you back the Gysin exact sequence for circle bundles. So I've been trying in the last 10 years to make sense of this for a different type of sphere bundles, so not only the circle, but higher dimensional spheres. And that's the reason why I started looking into subproduct systems. But let me now, since I mentioned spheres, go to the other extension. So this is Arveson's Toeplitz extension. Okay, so yes, so let's fix an integer d greater than 1, well, the greater or equal to 1, and then we can construct a Hilbert space. So it's called the Drury-Arveson space. We just take the completion of the polynomials, the commutative polynomials in d variables, with respect to the norm coming from an inner product, and the inner product is as follows: is z alpha z beta is almost always 0, except from when alpha and beta are equal, and then the length of that, that inner product contains some coefficients that are just multifactorial coefficients. So once you have this Hilbert space, you can define on it some multiplication operators, and you just take a function of several variables and you multiply with either of the variables independently. So it's like the unilateral shift, but now you do it in all the directions of the variables on which your function depends. And this collection of operators, altogether, these d operators, you call it the d shift on this Hilbert space. Okay, so this is one way of defining it, but there is a better way. Well, better, I mean, it's more commutative way to define it, is to realize that actually, this is something you know from algebraic geometry or commutative algebras, that the homogeneous polynomials of degree m correspond to symmetric tensors of order m. So by using the you can use actually the isomorphism and look at a different description of this Hilbert space. So you look at the symmetric Fock space. This is something that appears a lot in physics, and that's a subset of the full Fock space in d particles, if you want, in d dimensions, and it has an orthogonal projection from the full Fock space into the symmetric. So inside the tensors of order d, you select the symmetric ones, and then you have a projection that goes from the tensors, from general tensors to symmetric ones. It's a symmetrization kind of operator. And then you can look at compressions of the shift. So you take a symmetric tensor, you tensor it on the left with one of the generators of your finite dimensional space. This gives you a new tensor that may not be symmetric, so you make it symmetric by applying the projection. And this is something that in operator theory, as I said, is known as compression of the shift. And then the collection of operators T1 up to Td, where each of them is the one associated to one of the orthonormal basis vector. Now you call this a commutative D-shift. And of course, the reason why I put these two pictures simultaneously on the slide is because they actually describe the same object. Indeed, because of the isomorphism that you have between the Drury-Arveson space and the symmetric Fock space, then the D-shift on this H2 of D is, you can intertwine it with the commutative D-shift, so by using this unitary operator. So you can map one to the other, and depending on your personal taste, if you like homomorphic functions more, or if you like symmetric tensors more, you can look at one or the other picture. But somewhat the right picture is a bit nicer because of the commutativity. So in 1998, Arveson, in his multivariate operator theory 2, I think, paper, he proved that this collection of D operators has the following property, is commuting. I already told you that. So Ti and Tj commute. So you first shift and compress, and then shift and compress again in two different directions. You do it's the same operation. When you sum up Ti and Ti star, you get the identity minus the projection onto the vacuum, or the 0th level of your Fock space. And the operator is essentially normal, meaning that Ti star and Tj commute up to some compact operator. And the expression for the commutator between Ti and Tj contains actually the number operator, which is that unbounded operator that tells you when you apply to a tensor of a given length in which component you are. So it's the usual number operator from physics, I guess. Okay, and then Arveson proved the following, that if you look at the C-star algebra generated by the D-shift, then there is this exact sequence where the compact operators on the symmetric Fock space, or if you want on the Arveson space, he didn't call it like that, of course, sit inside the Toeplitz algebra, and then the quotient is commutative, of course, because I told you that they commute, and they commute up to compacts with the right joints, so quotient will be commutative. And the quotient is this commutative C-star algebra, is the algebra of functions on a 2D minus 1 dimensional spheres. So again, you can interpret the Toeplitz algebra of Arveson as a non-commutative disk, whose bound, or ball, maybe even it's a better word, whose boundary is a odd sphere. So, and now, this is the reason, as I said, I was interested in sphere bundles when I started studying subproduct systems. So I wanted, okay, now let's try to glue together these algebras across, along a C-star algebra to see if we can make sense of sphere bundles. I still don't know how to do it, but there's been some progress in related directions. So let me now introduce the subproduct systems of Hilbert spaces. So these were defined in 2009 by Chalit and Solel for correspondences, actually mostly for W star, but also C star correspondences. And around the same time, independently, Baat and Mukherjee defined them for Hilbert spaces. They have connection with dilation theory and free probability. Here I will just focus on a very specific case, which is the case of Hilbert spaces, and actually more standard subproduct systems of Hilbert spaces. So basically, this object consists of a collection of Hilbert spaces labeled over the positive integers, and there are isometries that map Ek plus m into Ek tensor M. So that's why they're called subproduct systems. So if you know what a product system is, there you have stuff like that. Well, over a semi-group. So when you tensor Ek and Em, it's on the nose equal to Ek plus m. This is a product system. More on this maybe later. Think K-graph algebras if you want. And with subproduct system, Ek plus m is only embedded into Ek tensor M through the isometry. And we call a subproduct system standard and this is a notion that you can give only for Hilbert spaces, when E0 is the complex numbers, then the maps that you obtain by embedding EM into E0 tensor EM, which again is EM, because you're tensoring with C, are just the canonical identifications. And then there is this associativity kind of condition, which basically tells you that if you start with something KLM, with label K plus L plus M, then there are two ways in which you can map it into the triple tensor product. So you can first do the first two legs, and then tensor EL, tensor EM. Or you could do it the other way around. You first do the last two legs and then the other one. And then, of course, this shouldn't matter. So the way you compose these maps, and this is exactly the expression that I wrote there, using the isometries. Okay, and what can you do with this? Well, you can do what we did before with the symmetric Fock space. You can do a compression of the shift. So you construct first a Hilbert space on which you want to represent your C-star algebra, the Toeplitz algebra it will be. And this is just the direct sum of all the Hilbert spaces given in your subproduct system. And then you define the Toeplitz operators by compression. So you start with some elements in element in EK and some element in EM, so psi and zeta. And then you take the tensor, you tensor with psi on the left, and then that thing may not be in your subproduct system, but you have this isometry, so you can always push it down to what you're in. So you go the other way around, you push it down to what you're interested in. Okay, and this gives you a family of operators on this Hilbert space. Then you can define the Toeplitz algebra just as the smallest C-star subalgebra of the bounded operators on f of e that contains all the shifts. So this is the prescription. And of course, if you're working with finite dimensional E1 and you have a standard subproduct system, meaning that all the higher Hilbert spaces will be contained in the tensor product of E1 to some power, then you can just work with the operators coming from orthonormal basis elements. And of course, you should be able to prove, and it's not very hard, that the choice of orthonormal basis doesn't influence your result, and it doesn't, of course. Okay, so can we say a bit more about these C-star algebras? Well, if the subproduct system consists of finite dimensional Hilbert spaces, then Wieselter proved in 2012 that the compact operators are an ideal inside the T of E, and then it makes sense to look at the Kunz-Pimsler-like extension and define the Kunz-Pimsler algebra as the quotient. If you don't have this finite dimensionality condition, things complicate a bit. So for instance, if you want to do it with the infinite dimensional Hilbert spaces, you need to quotient by a different ideal. But now, in everything that I will discuss, this is finite dimensional, so it's well behaved. And of course, I wouldn't talk about this if there was no connection with a symmetric Fock space. So if you fix an integer d and consider the symmetric tensors, that this gives you a subproduct system. And then if you mimic this construction, you get back the extension that I showed you before. So spheres are a particular case of C-star algebras of subproduct systems. All right. Now, for something completely different, I always liked algebra a lot. And when I was doing when I had my position in Leipzig, I started talking to some non-commutative algebraists, so I got to learn a bit about quadratic algebras and stuff like that. And then I discovered that Chalit and Solel have something very algebraic in their paper, which they call a Nullstellensatz for non-commutative polynomials. So basically, they claim that there is a one-to-one, they prove that there is a one-to-one correspondence between homogeneous ideals in polynomials in non-commutative variables and subproduct system of Hilbert spaces, like the one I described before. So just some algebra notation. We take a finite set of variables. We look at the free monoid it generates. It's graded by the length of the words. And then we take the free associative algebras with unit generated by this set of variables, and we call that the algebra of the commutative polynomials. So it's stuff like this: x1, x2, minus x2, x1, plus x3 cubed, square. I don't know. This is a non-commutative polynomial in 3 variables. And it is also homogeneous, as you see here. So we call a non-commutative polynomial homogeneous of degree m if it belongs to the degree m component of your free algebra. Okay, and then this is the theorem. If you have an n-dimensional Hilbert space with orthonormal basis, then you have a bijective inclusion reversing correspondence. That's what you want in a Nullstellensatz between the proper homogeneous ideals in the free algebra and standard subproduct system with E1 containing E. Actually, then you can also restrict to E1 equal to E. So just to give you an idea of how this works, so take this polynomial inside, take the idea that this polynomial generates inside C of x1, x2, x3. Well, you can identify this because, as I said, there is before I talked about the identification between homogeneous polynomials and symmetric tensors, but non-commutative polynomials correspond to general tensors. So you map this to E1 tensor E2 minus E2 tensor E1. You just look at the variables plus E3 squared. So if E1 is a span of E1, E2, E3, then this is a subset of E1 tensor E1, the span of this. So you go to the picture with the tensors, and now you can construct your subproduct system inductively. So you put E0 equal to 1, to the complex number, sorry. E1, as I said, as the span of these 3 vectors. So in this case, it's C3. And then you take E2 to be the orthogonal complement of what shall we call this? V. V orthogonal inside E1 tensor E1. And then you find a way to generalize this to higher dimensions by maximizing somewhat the construction. So you look at things that are orthogonal when you tensor with other vectors in all the possible ways. And if you want, this is the same as doing En equal En minus 1 tensor E1 intersected E1. Okay. But of course, this works if the ideal is just a general proper homogeneous ideal, so it can have component of different degree and can be much more complicated than this. So this is just a working example. But the idea is that whenever you have an ideal in the free algebra, you can look at the corresponding subproduct system. And then you can also look at the corresponding C-star algebras and try to understand what they tell you. And this is a bit more complicated than you would expect. So the reason why Charlotte and Soler were interested in this is that they wanted to understand the C-star algebra or the W-star algebra generated by a row contraction subject to polynomials conditions. So, and this works similarly, like you take an n-tuple of operators on a Hilbert space, you take a word of length m, and then you call t to the power alpha, the operator that you get by concatenating t1 to the power alpha 1 with tm with the power alpha m. And then if you have a polynomial, a non-commutative polynomial, then you can say that p of t is the linear combination of the polynomial applied to this n-tuple of operators. And then in their paper, they proved that you can interpret all these operator algebras and C-star algebras that they construct as something related to universal C-star algebras generated by a row contraction. But the way to really, but it's not true, this is something that it's not true in general, is related to the isomorphism problem. So at least in the commutative case, the tuplets algebra is the universal sister algebra generated by row contraction with polynomial relations, but in more general cases, this is not true, and it's an open problem to understand the precise relation here. But this should give you but the motivation that I had in mind is, okay, we have this set of operators that have some relations. Can we construct a representation of the sister algebra on a sensible Hilbert space? There are some examples in which this goes well, so I'm going to try to either give it as an exercise or no, I would just ask maybe the audience. So suppose you take a free algebra in two generators, so polynomials in two variables, then you quotient by the commutator ideal, you should get something commutative. Well, the resulting Kunz-Pimser algebra is the continuous function on the tree sphere, and the reason for that is that you have the two variables that generate the sphere, plus you have this row contraction relation that then becomes a sphere relation when you quotient by the compact. So you can describe the tree sphere as a subproduct system, as a sister algebra of a subproduct system. So if you do it in more variables, then you get back the same construction that I showed you already with the symmetric powers. So I mean, you're quotienting by the commutator, so it's the same as saying I kill whatever is antisymmetric. And then you get the odd dimensional spheres. Now you can say, okay, let's put some q's into the game. So let's take the first example, but then put powers of q. And I put q minus 1/2 and q 1/2. It looks silly. I could have put 1 and q. But the reason why I put it like that is something that we'll discuss in 5 minutes, maybe. So if you take that ideal, then the quotient algebra is what we saw yesterday, C of SUQ2. So it's this continuous function on a quantum group, or if you want, on a quantum sphere, and if you like dynamics, it's a subshift of finite type. And now if you quotient by nothing in C of x1, x2, then you get the O2, so you get the full two shift in the dynamic sense. So it's a Kunz algebra O2. So there are lots of nice sister algebra that appear as the Kunz-Pimser algebras of subproduct system, and that's why we started looking into them, maybe. Okay, so now I'd like to talk about something more recent, which are quadratic subproduct system. So I'm gonna go back to algebra. We start with graded algebra. Locally finite dimensional means that all the fibers are finite dimensional vector spaces. Then you look at the tensor algebra, and algebraists say that the algebra is one generated if the map that you get from the tensor algebra into A is surjective, meaning that you can write any element of the tensor algebra, any element of your algebra as some tensor with the elements made out of the elements of A1. Oh, there should be an end there. First typo is spotted. Probably not the only one. And then one generated algebra is called quadratic if the kernel of this map is quadratic, meaning that it's a subset of A1, tensor A1. So basically, when you study quadratic algebras, you just have the following ingredient. You have a vector space, and then you have a subset of the tensor of the vector space with itself. Okay, and then I proposed this definition. I mean, I don't know if it will ever end up in a paper, probably. Subproduct system of finite dimensional Hilbert spaces is quadratic if there exists some subset of E1 tensor E1 such that E is isomorphic to the subproduct system that you construct with a recipe like this, or if you want, that you can map this the subset W to a collection of polynomials that are homogeneous of degree 2, and then you do the Nullstellensatz. All right. So why quadratic? Well, first of all, quadratic is very natural in the non-commutative world because we often write out commutators between operators and look what they are. So I don't know if I can think of any sister algebra that I know that it's not given by quadratic relations, but exercise maybe. But so we started looking at this with Jens. It took a long time, but it was published in 2021. while looking at SU2 representations. So we started with the finite dimensional representation of SU2. Of course, the reason why we did this was that SU2 is a three-sphere, so we wanted to understand the spheres. And we defined the determinant of the representation to be the isotypical component of the trivial representation inside the tensor of the representation with itself. So if you want, they are the elements of the double tensor that are left invariant by the diagonal map applied to the representation. Oh yeah, I don't know why there's a tau there. It should be a rho. Oh, sorry. I'm really sorry for my typos, but okay, you can, tau is equal to rho in this slide. Okay, so what we proved is that if you start from something that is an irreducible representation, that it's just character formula, then this isotypical component of the trivial representation in the tensor is one-dimensional, and then we wrote out what the generator for this vector space was, and this was an alternating sum of tensors of ei and en minus I plus 1. So basically, if you go back to the polynomial picture that I mentioned before, this corresponds to this particular polynomial, minus 1 to the I times xi xn minus I plus 1. So if you do it for n equal to 1, so the first irreducible representation, which is two-dimensional, then the polynomial is the commutator. So consistent with what we described earlier. Okay, so we constructed the quadratic subproduct system, and as I said, the higher fibers have this property, and we constructed the corresponding sister algebras and obtained an extension that is SU2 equivariant, because everything we did started from the ingredient of an SU2 representation, so we could make all the spaces equivariant. Okay, and then we proved some stuff about this, so I'm gonna go a bit quick about this, but basically we proved that whenever we started from an irreducible representation, then tensoring two of the Hilbert spaces in our subproduct system gave us a decomposition that was the same as the fusion rules for irreducible representation, but here the elements appearing may not be irreducible. So it was just a general pattern that we saw, that we could always decompose ek plus m into a sum of lower label Hilbert spaces, but they may not have been irreducible. Actually, they were not in general. So it was quite puzzling for some time. I talked to Makoto at some point. He mentioned temporary lib. I was very baffled by the comment, but then later I understood what he meant. But so we were also able to compute the dimension of all these spaces. I mean, it's not a very complicated thing once you know what you're starting from, but they satisfy the nice recursive relation. And well, I spent quite some time on the online encyclopedia of integer sequences playing with these dimensions, and then I saw the pattern, and it was very exciting. Of course, everything was already there. But when you look at the sequence of the dimension, then you can try to define the analog of a number operator, and this is what we did. We defined this operator that we called phi. It's defined on the Fock space, and it maps xi to xi times the ratio of the m by the m plus 1. This seems a bit arbitrary here, but it has, if you look at how everything is defined, you immediately realize that it has very nice properties, because if you define gamma to be the limit of that ratio, then phi minus gamma, the identity, is compact. So you can write down, and this slide is very full, and I don't need you to grasp everything, but then you can write down what the kind of commutation relations the operators in your Toeplitz and your Kunz-Pimser algebra satisfy. And these are, so the first one, I'll just ignore my own typos. The first one is the usual one, so the fact that it's a row construction, so it's 1 minus the projection. The second one comes from this this polynomial that I gave you before. And the third one and the fourth one, they look a bit weird, but if you have this ratio of dimensions, and if you apply it to n equal to 1, you get back exactly this Arveson Toeplitz algebra. So there you had the number operator because the dimensions are always n plus 1, n plus 2. But here the dimensions behave differently, so you need to take care of that. And then this phi operator has such a very nice properties, plus gamma is a solution of that quadratic equation. So then you can write down the commutation relations in the quotient very easily. Of course, we were not satisfied with just the C-star algebras. We wanted to compute the K-theory. Then this took a long computation. But basically, we were able to simplify the exact sequencing K-theory coming from the defining extension to a sequence like this that only contained the K-theory group of the complex numbers and the K-theory group of the Kuhn-Spimser algebra. And then which was what we were after, what we found is that the map in the middle was the sum of 3 terms. So 1 minus the class of the representation plus the class of the determinant, and this may now explain why we called it the determinant. So basically it's, if you think about rank 2 vector bundle, this is the Euler class, vector bundle, V, or E actually. And chi of E is minus the class of E plus. And that's a determinant line bundle. And in general, for a rank n vector bundle, then chi of E is 1 minus E plus lambda square of E minus, and you go on like this, blah, blah, blah. So it's the alternating sum of the classes of the wedge powers of the bundle. So then we say, okay, we got the Euler class, nice. Of course, now this Euler class is just a number in this case, but it's really what we were after. And then you can compute the K-theory groups of this Kuhn-Spimser algebra, and they are quite some torsion in K0. And then, regarding the comment about the fusion rule, then later Abestad and Shveyev wrote a paper, well, 2 actually, on C-star algebras of subproduct systems with quantum group symmetries. And they gave the following definition. They said that a quadratic polynomial in n variables is a temporally Lieb polynomial if it's of that form. Haha. So it's an alternating sum of xi, xn minus I plus 1, and the ai's, the coefficients in front, satisfy some condition that makes the absolute value of that product equal to 1. Of course, I don't need to tell you, if you put ai equal to either minus 1 or plus 1 like we did, then you get a temporary polynomial. So ours was a very special case of theirs. And then they considered the subproduct systems associated to this polynomial. And what they proved was that not only, so we had proved that there was an SU2 equivariance going around, but they proved that there was something more. So if there was an action of the free orthogonal quantum group defined by an anti-diagonal matrix with entries the coefficient in the polynomial. And then you got that everything was OP plus equivariant. And moreover, they also proved that the algebras are nuclear. And this I put here because I may discuss it in 5 minutes. They also observed a connection with the theory of quantum groups and representations thereof. So they proved that the algebra, the Kuhn-Spimser algebra, is isomorphic to the linking algebra, or if you want, the Bi-Galois object, in the sense of Bichon, de Reit, and Vaas, of these 2 quantum groups. SU tau Q. Tau is a parameter, I'm not going to describe it now, but it depends, it can be constructed out of the AIs. And the other group is the free orthogonal quantum group that I mentioned earlier. So these two quantum groups have the same representation theory. And then you can construct the Bi-Galois object that implements this, the fact that they have the same representations. So in particular, our commutation relations are a consequence of this fact, because there is an explicit description of these linking algebras in terms of generators and relations. They also proved is that the embedding of the complex numbers into the tuplets algebra is a KK equivalence, like we did, but they proved it with an OP plus equivariance. And they used Baum-Kohn for SUQ2 for proving this. So they had a much shorter proof than we had. And using that, you can now, they also remarked that the Kunz-Wimser algebra is the boundary of the dual discrete quantum group of the free orthogonal quantum group. So some sense, if you go back to the think back of the picture that I showed you earlier, again, we have a picture, we have an interpretation of the quotient algebra as some boundary algebra. Okay, and then of course, well, shouldn't be otherwise, but you can compute the K theory and K homology groups, and they are the same as the one that we had recovered. Okay, so how much time do I have? 8 minutes or something? Okay, great. So, so then we, of course, well, I don't know exactly how this came about, but Dimitris Gerontoyannis has been a postdoc in Leiden for some time, and he's very interested in Poincare duality, KK duality. So we started talking about whether there was a way to describe the KK duality that we suspected this algebra satisfied in a quite explicit way. So let me remind you of what KK duality is. So it's this notion that was introduced by Kasparov that basically generalizes Spanier-Whitehead duality, or if you want, Poincare duality, which is the duality that relates the homology of a finite complex with the cohomology of some dual. You can make sense of this notion in KK theory. So you can take so you can say the two C star algebras separable are KK dual if there are two classes. First one in KKI of A tensor B with values in C, and the other one in C, from C to A tensor B, such that you have this, so the Kasparov product of those classes satisfy this condition. And now there is a -1 to the power I because you have to take into account some possible dimension shift. So what's the consequences of a KK duality? Well, that there is an isomorphism between the K theory group of one algebra and the K homology group of the other, with possibly some degree shift. Okay, so let's go back to our sister algebra. So the tuplets extension, as I said, is there. And then Abessad and Neshveyev proved that the algebras were nuclear. So in particular, the extension is semi-split. Which means that if you look at well, I haven't really showed you how we proved that we had the Euler class, but there was an identity of KK classes. So this could have, same arguments can be applied to that exact sequence in the temporary Lib case to simplify the map appearing in the K homology exact sequence. And then if you compute the K homology group of these algebras, then they have a degree, they are the same as the K theory group that I showed you before. Oh, no, it's correct. Okay, no, it's correct. But now, I thought I saw a 1, but it's a 0. It's fine. They're the same, but now there's a degree shift. So before we had torsion in K0 and Z or 0 in K1, and now we have the opposite for K homology. So we should expect a KK duality of degree 1. Okay, and to construct the KK duality, we actually proved that OP is a self-KK dual, but we did this like in a bit in the way that Kaminker and Putnam do it for Kunz-Krieger algebras. So we constructed a different algebra that then turns out to be isomorphic to the original one. So we defined an operation on the polynomials that gave us a new algebra that actually was isomorphic to the original one, but that allowed us to describe the KK duality in a more concrete way. And so basically starting from a polynomial of this form, we defined the polynomial that we call P dagger, and we just swap the indices of the metrics that give you the polynomial. So this is in a bit more general setting than what I described earlier as temporary Lib. But yeah, so if the matrix is this anti-diagonal thing, then it also, of course, it's a special case. And then we proved that the Kuhn-Spimser algebras defined by these two polynomials are KK dual with dimension shift 1. Okay, so the proof relies again on quantum group theory, on a monoidal equivalence between some other quantum group. It's an extension of the OP class that I described earlier, which works also with with matrix that have these properties, and the quantum group UQ2. So basically, by using this monoidal equivalence, we reduce the proof to the case of the polynomial that I showed you before, the one, the q minus 1/2 and q plus 1/2. And proving it there, we obtained it through monoidal equivalence for all polynomials that have this form. Okay, so let me summarize and talk about some possible open questions that we have. So the first thing that, of course, one will want to do, comparing with the work we did with Jens, is try to understand what happens if the representations you start from are no longer irreducible. And the other question that I've been thinking about, also with my PhD student, is how to incorporate construction that you naturally have in the theory of quadratic algebras, like free products and Segre products, Veronese algebras, and so on, into this setting. So what happens if you do the subproduct system of a Segre product of two subproduct systems, stuff like that. The reason why this is there is because when we have multiplicity-free representation, we can draw up an explicit connection to free products of Hilbert spaces and C-star algebras. This is a work in progress that we hope to write up soon. And then, of course, playing with all these dimensions of sequences, we found some connection between the Euler class and the generating function of the Hilbert series. It's circumstantial evidence, so there seems to be a deep relation, but needs to be proven why there is. And now, of course, you can also go in other directions. So you can wonder, okay, there are all these quantum groups acting on these subproduct systems. Can we prove a gauge invariant uniqueness theorem, like the Kuhn-Spimser algebra one for U1, but with these different symmetries? Oh, other typo. Then you can extend try to work with higher rank groups. And ideally, it would be nice to be able to glue stuff together along a C-star algebra, so just do SU2 correspondence. But this requires more care when you work with complementability in Hilbert modules. So like connects to a problem that Bram Mesland and Adam Rennie worked on a couple of years ago about two projections in Hilbert C-star modules. But this is for another project. So I will finish here, and thank you for the attention. And I finish with a quote by Thomas Mann. I think it's excellent for this. Thank you.